All right, so for this simple example, once I reach 100, then I start to fall, okay? And I'm going to fall at what rate?
Negative 20 dB.
Negative 20 dB per decade. So that basically, I'm going to put a negative 20 right here. Here's 1,000. This guy's going to be falling like that. Now, if I were to go into MATLAB and make a Bode plot of that, what would be the difference between what I'm showing right here, my approximate, and the actual? So if I ask MATLAB to do the Bode command, I say Bode of that transfer function, MATLAB will draw the actual honest-to-God Bode plot, meaning what it'll show on a log scale is 1 over the square root of omega over 100 squared plus 1. It'll draw that. It'll draw that on a log plot. What will be the difference?
It's not going to be as 3D.
It will be exactly as linear. But there's one area where there's going to be a difference.
It's not going to be a sharp cutoff. It's going to be curved.
Yeah, it's going to be curved right around the breakpoint, right? So it's going to be basically exactly correct, almost exactly correct, except, in fact, it'll even be closer to what I'm showing here. So it'll look like this. It'll go around, and then they'll match up off here. So right in this region, right around there, there's going to be a discrepancy. Only there, all right? So if I ask you, and this was the thing, so I asked you, well, what's using, in the last homework and this homework, I said, using your approximate curve, look at omega equal to 100 and tell me the magnitude. If you plugged in S equal to J 100 into this thing, it wouldn't have worked, right? You would have been off. In fact, you would have been off by 3 dB is the difference at that point, okay? So use your approximate curve when it says to, okay? The magnitude is basically what I do is I take the value of this curve, right? And I say, okay, so if I'm asking you for the magnitude at 1,000, right? The magnitude at 1,000 would be negative 20 dB, all right? That's the value there. The y-axis value there is negative 20. The slope also is negative 20 at that point, but the y-axis value there is negative 20. So if I want to know the true magnitude, I would say, well, 20 log 10 of the magnitude of h of j 1,000 is equal to negative 20. So turn that into the true magnitude. So I got to divide both sides by 20 and all that. I would find that the honest to God value there would be 0.1. Okay. For 100, it would be 0, which means that the magnitude would be 1. All right. In terms of an input-output relationship, this means that the output would be 0.1 times the input at that frequency. Okay. All right. So we're going to do that all here with this particular transfer function, but let's make sure we're on the same page. All right. We don't want you guys to arbitrarily fail the test on Friday. So if we need to take a little bit more time, let's do it. Okay. All right. So, all right, there's our transfer function. All right, this guy here. How many zeros does it have? 2 zeros. All right, somebody online, how many poles?
3.
3. 3 poles, 2 zeros. Okay. So, all right, where are they located? Where are my zeros located?
Negative 0.1 and negative 100.
Negative 0.1 and negative 100. All right. So I got a pole in this case at negative 0.1. I'm sorry, not. I have a 0 at negative 0.1. And a 0 at negative 100. Okay. So there's a 0 here and here. Negative 100 and negative 0.1. Okay. What about my poles? Where are my poles located? 2 of them are at 0. So I'm going to say I got one at 0 and I got another one at 0. So there's basically 2 of them here. So I'm going to try to denote that. I'm going to say x squared right there. Okay. All right.
You can have the same pole twice.
Sure could. Yeah. In fact, let's do it. Let's show a circuit that could do that. All right. I'll show you a circuit that can do that at the end. All right. So if I have,
Negative 200.
where's my other pole?
Negative 200.
Negative 200, negative 200. All right. So I got 5 things in total that I'm dealing with there. Okay. All right. So in this case, given that, all right, where am I going to go? And so I guess I can put those on here. So negative 200 there. Actually, you know what? I want this to be at 2000. That's actually what I did my math for. All right. So I changed it. I changed that to 2000. All right. You guys follow me there?
Yeah.
Yep.
Okay. All right. All right. All right. Well, so let's copy this over. I'll copy these values over, right? So I'm on my step 1B. I want to get to my breakpoints. Now that I got my poles and my zeros. And of course, yeah. All right. I've got that. So how do I get to breakpoints? What are the breakpoints that I would have that correspond to the poles?
Absolute values.
Absolute values, yeah. So 0, 0, and 2000. It's really 0 and 2000, I guess, right? But it's not on a test. I wouldn't be too. If you told me 0 and 2000, you told me 0 twice, I'd take it either way.
Wouldn't that just
Now, what would it be for the corresponding breakpoints from the zeros? 0.1 and 100. Okay. All right. So that tells me basically that when I look at the Bode plots, there's going to be changes that are happening at what frequencies? At those breakpoints. All right. At those breakpoints. All right. So that's good to know. All right. Now, here is our standard form, our step 2. Let's copy this guy over. All right. All right, so there's our original transfer function, and we want to get that in standard form. It's not. All right, getting this in standard form is a pretty trivial thing to do. What is it? What am I doing here? I'm just doing basic algebra here, right? So I'm saying h of s equals negative 10 times what?
100 outside on the top and 2000 outside in the bottom.
Yeah, so I got to factor out 0.1, 100, and 2000. Okay. So let's look at the s plus 0.01 first, right? Isn't that just going to be 0.1 times 10s plus 1? Right? You guys following me there? Right?
Yep.
If I did 0.1 times 10, what's that equal to? 1, right? And 1 times 0.01 is 0.1. All right. So that is, you know, I did my math there. What would I do with the s plus 100 term? What would I factor out?
Factor out 0.01.
I'd factor out 100.
Yeah.
Right? I
Oh,
factor
wait, yeah.
100, and I'm going to get s over 100 plus 1. Right? So if you distributed that back in, you would have s plus 100. All right? Just basic, I don't know, what is that? The distributed property, I guess, in algebra, right? So s squared. And then what do I do with this s plus 2000?
You're going to pull out a 2000.
I can pull out a 2000. Yeah, 2000. And then I'd have s over 2000 plus 1. Like that. All right. So if online, then I ask you for, you know, what are my tau values or whatever. So if I look at this, my tau p values would be 1 over 2000. Okay. And my tau z values would be 10 and 1 over 100. Okay. Okay. All right. So when I'm looking at this, then if I want to figure out what my k value is, right? My k value in this case would simply be all the multipliers, right? The product of all those things. So negative 10 times 0.1 times 100 divided by 2,000. Like that, right? That would be my K value. And that's actually not too hard to do. I think that works out to negative 0.05. If I'm not sure, I've got a MATLAB program where I did that, negative 10. So I did a couple of things here. So let's see. So let's just check that real quick. So my K value, negative 0.05, okay? Now, that turns this thing into negative 0.05 times 10s plus 1 times s over 100 plus 1 all over s squared times s over 2,000 plus 1. Okay. Any questions about what I did there? Okay. Now, there's a negative sign in the front. What's the negative sign mean? No, that's why I asked. I set them up for that.
Shift to the down on the.
It does not mean shifted down. No.
This means our poles are going to go up, right?
So what do we? Okay, this is why I want to. So what are we plotting? What are we doing at the end of the day here? What is the goal? So we got a transfer function, came from a circuit. All right. What are we doing with this thing? This thing is a transfer function. It tells us the relationship between an output voltage and an input voltage, let's say in a circuit, okay? And it tells us at a specific frequency what the relationship is between the input and the output. In other words, if, just for sake of argument, if the magnitude at the frequency 100 radians per second, let's just say is 0.01, then it tells us if we put in 1 volt, what are we going to get at the output?
0.01.
0.01. If I put in a 1 volt input at 100 radian per second, I'm going to get 10 millivolts out, 0.01 volts out. That's what it tells me, okay? That's important, right? When we're talking about filters and all that kind of stuff, this is a very common way for us to think about it. So this H of S is a complex number, right? So if I have a complex number, negative 0.05, what is that complex number? Negative 0.05 as a complex number is what? In polar form. What is that in polar form? Well, it's got a magnitude, right? What's the magnitude of negative 0.05? 0.05, and it's got an angle of
Negative 90.
180. Right? It's got an angle of 180 degrees. So if you take the magnitude of that whole thing, what's the magnitude of negative 0.05? 0.05. It has an angle of 180 degrees. That -1 means that there would be a phase shift, right? It means that if I put in, if let's say I said, you know, H of J 0, right? If I plug, so what's the magnitude there? I don't know what I'm going to get exactly, but let's say it's negative 0.1, right? Negative 0.1, right? That means if I put in 1 volt, I would get negative 0.1 volts. Okay. Well, the magnitude wouldn't be that. Let me put it that way. All right. If the actual value of the transfer function is negative 0.1, that means its magnitude is 0.1 with a 180 degree angle. Right? That's what that means. You guys talking about a negative shift is what I do is I take the log of the magnitude. Once I take the log of the magnitude, if I'm taking the log of a number that's less than 1, I'm going to shift down. If I take the log of a number that's greater than 1, I'm going to shift up. Okay. That's what you got. You guys are skipping ahead a step when you say I'm going to shift it down with that negative. That negative number goes away because I am plotting the magnitude. If I plot the magnitude of that whole thing, that negative number is gone. All right. Everybody straight on that? If it had been -5, then when I do the shift later, it's going to go up because I'm shifting by the log of 5. Okay.
The example you have up there with the, you know, you put in like, you have the 0.01 equals the magnitude. You said if you
So we've got a specific set of numbers that we'll look at for this guy, right? So let's get through to that. Let's make the graph and then let's apply some real numbers to it. All right. Okay, so let's do this left to right, doing each individual one. So I want to start with the poles at the origin. All right. So the poles at the origin, there's two of them. All right. So if there's two of them together, I could do each one separately, but that's kind of annoying. I want to do them together. So if I have two of them separately, or sorry, two of them together, two poles at the same location, what's that going to do?
It's going to double the slope.
Double the slope. So they're going to be falling at negative 40 dB per decade. Now, every time I have something going through the origin, so here's my graph right here, and I didn't label for myself. This would be 1, 0.1. This would be 0.01 or 10 to the minus 2. This is 10. This is 100. This is 1,000. This is 10,000. That's 100,000. Okay. And I've labeled up my y-axis there in steps of 20 dB. Okay. And it makes sense for me to do 20 dB because if you think about it, 20 log 10 of 10 to the power of n. Right? If you did n equals 0, that's going to be 0. If you did n equal 1, that's going to be 20. If you did n equal 2, that's going to be 40. If you did n equal 3, it's going to be 60. And so my y-axis always marks itself off in steps of negative 20, like that. Negative 20, 0, 20, 40. On the exam, I will give you log paper like this, and I will mark up the units on the axes so that we mitigate the confusion. All right, I'll give you the major axis values, at least, like in other words, 1, 10, 100, 20, 40, 60, 80. I will mark those for you. All right, so that way we don't squibble over that during the test or after the test. Okay. All right, so let's start out with the two poles at the origin. So omega equals 0. Where is omega equal to 0 on this axis again?
Negative infinity.
Negative infinity, way off to the left side. All right. Okay. So in this case, what we said is when I have poles or zeros at the origin, they always come through at this point right here, right? Where omega equals 1. They always come through where omega equals 1, right? Because if I think about it, they're basically, if I plug in 20 log 10 of omega, in this case, they would be negative, right? And it's specifically because there's two of them, it would be negative 40 log 10 of omega. That's what I'm plotting. That's the line I'm plotting, would be negative 40 log 10 of omega. If I plug in omega equal to 0, right, this would be negative infinity. If I plug in omega equal to 1, what would this equal to with omega equal to 1? Be 0, right? Be 0. The log of 1 is 0. All right. So that means that guy's always going to cross through the origin on this log scale. Okay. The origin on the log scale. So be careful about that. All right. So let's draw those two guys. How would I draw their effect here? Moving left to right. So let's say I started here at 10 to the minus 2. At 10 to the minus 2, where would that guy be?
0, negative
80.
40.
It would be at 80. Okay.
Oh, damn. Yeah.
And then at 0.1, he would be at 40, right? Because he dropped 40 dB in a decade. And then he'd be right here at 0 dB. And then he'd be right here. And then he'd be right here. And then he'd be right here. Okay. So let's draw that.
Is that because of our K value?
Nope, has nothing to do with K. This is the poles, the two poles at S equal to 0.
And it's negative because it's negative 40.
There's nothing negative. Oh, you see the slope is negative? The slope is negative because we're doing poles. Poles have a negative slope after the breakpoint. The breakpoint for this guy was somewhere at negative infinity. All right. So this is quite simple to think about it, right? There's basically for us 4 building blocks, right? If you look at this, if I have a pole at the origin, it says right here at omega equal to 1 is where that guy crosses through 0 dB. If anything, remember that, right? He crosses through 0 dB at omega equal to 1, okay? Basically everything is just a matter of these 4 building blocks: the 0 at the origin, the pole at the origin, the simple 0, and the simple pole. All right. We plot those building blocks and we just build with them. Okay. And then at the end, we deal with this K. Okay. All right. So back to where we were. Okay. So those are the 2 poles to do. I did them together, right? Because they're at the same point. When they're at the same point, basically I have 2 of them together. So instead of being at negative 20 dB per decade, it's at negative 40 dB per decade. Okay. All right. So now let's go ahead and do one of the other ones. Okay. So let's do the pole at 2000. All right. The pole at 2000. All right. So my pole at 2000, that basically is here. All right, is 2000. You don't need to worry so much about, okay, I know what a log plot looks like because I've looked at it for many years, but 10 to the third, this is 2000, this is 3000, this is 4000, this is 5000. You don't have to be that exact about it. You know that it's somewhere between 1,000 and 10,000. All right, so there it is right there. All right, it's the first division after 1,000. Okay. What happens for frequencies lower than that?
They drop 20.
Just
Frequent-
0.
For frequencies lower than that, it's 0. For frequencies greater than that, it drops at 20 dB per decade. So that means he starts to fall here at 2000. At what point is he going to reach negative 20 dB? At what frequency will he reach negative 20 dB?
20,000.
20,000, right? 1 decade. At 200,000, he'll be at negative 40 dB. All right, so I'm going to draw this guy in here like this. Like that. All right, and he's 0 below that. I'm not even going to bother drawing in the 0. He's 0 before that, and he starts falling. Okay. All right, now let's do the zeros. We've got 2 zeros to worry about. Where was the first 0?
Negative 0.1.
Yeah, negative 0.1. Okay, negative 0.1. So what happens for frequencies below 0.1?
It's just 0.
Just 0. What happens for frequencies greater than 0.1?
Rises at 20 dB per
Rises at 20 dB per decade. Okay. All right, so he's right here. All right. And at 1 radian per second, it would be at 20 dB. I should be doing a different color again. We'll do the orange here. All right. So there's this. Where would he be at 10 radians per second?
40.
40, then 60, then 80. Okay. So it's going to go like this. Okay. What about the other pole? Actually, the other 0, sorry. The other 0 is at omega equal to 100. All right, so where would I be for that? Omega equal to 100. Well, that's here. Okay, so let's do, I don't know what we're going to do with that. We'll do a green. Okay, just a puke green color. All right. Now, this guy's a 0, so for frequencies lower than the 0, it's what? For frequencies lower than the 0, it's what? 0. Frequencies greater than the 0, it's what?
20 dB raising.
20 dB rising. So that means at 1,000, it's at 20 dB. At 10,000, it's at 40 dB.
So why
At 100,000, it's at 60 dB.
Why did we start at 0 at negative 0.1, but that 0 we started at positive 100?
We didn't. All of these numbers are positive. There is no meaning to a log of a negative number, right? So this is an important point that he's asking, right? The values of S, right? When you look at this transfer function, the values of s that make this thing 0 or infinity are negative numbers. They cause effects at positive frequencies because we are plotting the magnitude of h of j omega. There is nothing at all negative on any of this graph because what are we looking at? On this graph, we're looking at positive frequencies and we're looking at magnitude. What's confusing about this is once I take the log of a number, the log of a number is negative if that number is less than 1. So 0.1 is my breakpoint. My 0 was at negative 0.1, but the breakpoint was at 0.1. Now that looks to you like it's negative because it's on the left side of that line, but it's not negative. It's
more of a number line situation.
it's a logarithmic line, and you know, so basically anything that's negative on a log scale just means you're talking about a number less than 1, right? Like if you plotted back to, you know, high school, right? If I plot the log of x, the log of x looks like this, right? For any number less than 1, it's negative. For any number greater than 1, it's positive, right? That's why we're seeing negative numbers on these scales, right? I think what screws people up is the logness of this is part of what screws people up, okay? All of the frequencies I'm dealing with are positive. All the magnitudes I'm dealing with are positive. I have negative numbers because of the logarithms. Okay. Okay. So then I have to add those things up. All right. So before I start trying to add stuff up, any questions about what I've got so far?
Quick question. Why is it negative 40 instead of the 20?
For the why is what negative 40?
Negative 40 log base 10.
You're talking about for the poles at the origin?
Well, yeah, I'm confused on the 2 poles at s equals 0.
So what I could do if I wanted to is I could say, well, I've got 2 poles that they're both falling and they're sitting right on top of each other at negative 20, but I just combined them right out of the gate. Okay, so in other words, there's one going negative 20 log 10 of omega, and there's another one going negative 10 log, or negative 20 log 10 of omega together, right? So the summation of those two is negative 40 log 10 of omega. If I
Okay.
just had one pole, then it would be negative 20. Because I have 2, I add them up. And I just skipped straight to that step of adding them up right off the bat.
Okay, thank you.
Is that
Yeah, that's pretty simple.
okay? All right. All right. So now the process of adding them up, this is always a little bit trickier than it needs to be. This whole idea of I move left to right. The way that I do this is I look at the first one that's not 0. So going left to right, what's the first one that's not 0?
Oh,
So the poles, it's the poles at s equal to 0. They're falling as I move left to right. Okay. So what I typically do is I look at it like this. I start out knowing that I'm falling off. As I move from left to right, I start out knowing that I'm falling at negative 40 dB per decade. And then I look at where are the breakpoints. And then I think to myself, how many poles and zeros are active between those breakpoints? When I say active, meaning that they're rising or falling, they're not flat, right? So if I'm looking here, let's say between 0.1 and 100. All right, between 0.1 and 100, what do I have? How many poles between 0.1 and 100?
2 poles.
2 poles and how many zeros?
2.
2 poles, 1 0.
Oh, you don't include the one at 100.
Oh, the 0 is the orange one, right?
There's 0.1. Okay. So I'm starting out falling at negative 40 dB per decade. Then I reach a breakpoint at 0.1. At 0.1, I reach a breakpoint that comes from a 0. Okay. So at that point, I have 2 poles, 1 0. So the combined effect is a negative 20, a negative 20, and a plus 20. So what's my slope?
No, no.
Negative.
Now
Still
negative 20. Negative 20. And I'm going to stay at negative 20 until I get to another 0. At that point, I have a positive 20, a positive 20, a negative 20, and a negative 20. So what's my slope then?
0.
0.
0.
Right? Then I reach at 2000, another pole, which is going to push my slope to
Negative.
negative 20. Right? So I'm going to be at, because at that point I got 20, 20, minus 20, minus 20, minus 20. Right? You add that up and it's going to be negative 20. Okay? So let's follow that. The way that I do that is, if to do that total curve, all right, I'll do a purpley thing here, right? So I'm going to follow this guy until I get to here. At that point, I reach a break point. So my slope is going to go down from negative 40 to negative 20. So then I'm going to hit 20 dB there. I'll hit 0 dB at 10. And I'll hit negative 20 dB at 100. Okay, so let's draw that slowly. Like that. You guys follow me? All right, my line's not particularly straight, but you get it. All right, I reach another break point there. That break point is 0. So adding a 0 does what to my slope?
Makes your slope 0.
Yeah, it
Cancels
increases.
it out.
Yeah, so it increases my slope by 20, which in this case is going to mean that my total slope is 0. So I'm going to be, I really can't draw a straight line here. It's going to be 0 to the next break point, which is there at 2000. At 2000, I hit another pole and I fall 20 dB per decade. Yeah. So that means that I would be at negative 40 here at 20,000. I'd be at negative 60 there at 200,000. So let's draw that up. Be like that. Okay. You guys follow? So the slope here is negative 40, negative 20, 0 there, and negative 20 here. Okay. You guys follow what I did?
Yep.
Yep.
Okay.
A quick question. If the poles were negative, the slope would be positive for the 0, right?
If the poles were negative, I don't know what that means.
So if the two poles are 0, if it was negative, just say 10, would the slope go the other direction? Or is 0 always going? Well, because I guess my confusion is we've drawn the zeros across the origin the other direction before.
If I had zeros at the origin, I would have a positive slope coming from those. Like if I had S squared, I'd be rising at 40 dB per decade from those two poles.
Okay.
Or two zeros.
Okay.
Okay. All right. Yeah.
I was just asking, so for what we were talking about before, like the magnitude at each point would just be the y value.
The magnitude at each point in dB, all right, would be whatever my y-axis value is. That's right. Now that's not the magnitude. I got to undB that. All right. I got to get that out of dB and get that into the true magnitude, which means I got to do some more math, right? Which we'll do that math in a second. All right. Once we get this guy all finished up. Okay.
Okay, so I'm sorry. Maybe I'm reading this. Two poles at S equals 0.
Yeah.
Now, where's the 0 exactly? That is
what do you mean? Where's the 0?
0.1 and then 10 to the second, right? Those are my zeros.
Yes, that's right.
Okay, sorry. Yep.
That's right.
We're good. We're good.
Okay.
Thank you.
All right. All right. All right. So now what I want to do is I have one step left, right? What have I not done here?
Add k into the equation.
I gotta do that shift, right? I gotta add that shift in. So the shift was, I had this k equal to negative 0.05. All right. So if I do 20 log 10 of the absolute value of negative 0.05, because remember, it's a magnitude, right? That works out to be negative 26 something. What is it?
26.02.
Yeah, something like that. All right. Negative 26.0206. Negative 26.0206. Like that. That means shift the whole graph down, the whole entire thing by negative 26.0206. Now that negative in front of that has nothing to do with that negative 0.05, right? Because I take 20 log 10 of the absolute value, right? This thing's a magnitude, right? I'm taking log of a magnitude, right? So what would I do? Well, what I would do is, in my mind, what I do is I take this guy, I take the purple, which is the combined, and I know that between 100 and 2000, for instance, that guy was sitting at 20 dB. So what do I do there? Shift that down 26, okay? Shift that down 26. So between 100 and 2000, I would go, so here's, go back to black. All right, this is 10, this is 100, this is 1,000, this is 10,000, 10 to the 4th, 10 to the 5th, okay? So between 100 and 2000, I should be at, I don't know, negative 46. So that's, I don't know where that is. It's somewhere around here. All right, like that. That's about negative 46. All right. So what I do is I just look at some special points then, right? So I don't know. Another special point for me to look at would be this guy right here, right? That break point there. Previously, this break point at 0.1, I was at 40 dB per decade. So where would that be now? It wouldn't be at 40 dB. Where would it be? It'd be at 40 minus 26. All right, so 40 minus 26 is about 14 or so, right? So that would be somewhere around like here, I guess. Okay. So what I would say is this guy is going like this, leveling, and then falling at 20 dB per decade like that. And then before that, he's fallen at 40 dB per decade. So that would be, oh, over here, that would be somewhere like this. Right. And I don't, beyond that, I don't worry about it too much. Right. You guys can, don't need to worry about that too much. All right. You guys follow what I did there. Right. I shifted the whole thing down. Okay.
So can you, 10 to the 0 is 1, right? 10 to the 0 is 1.
Mm-hmm.
So what's the difference between a pole at 0 and a pole at 1?
Oh, infinitely many decades.
It's just
A pole at 1 is at 1 radian per second. A pole at 0 is at 0
but
radians
isn't
per
the
second.
origin at 1? Like the origin
No,
is 1.
so
right?
so the problem is you're getting too lost in terms, too lost in terms, right? So basically, what's this is a log scale. What you're looking at right now is a log scale. The origin on that log scale is 1 radian per second. This is when we talk about a pole at the origin. What we mean is that it's true. This, when I'm looking at this scale, there's no logarithmics going. There's negative numbers, there's positive numbers, right? If I have a pole at the origin, I have a pole at 0. That pole at 0 on a logarithmic scale is at negative infinity, right? So the thing that you're mixing and matching the two things. You can't mix and match those two things, right? That's what's causing problems, I think, for a lot of people, is that you're mixing and matching the log scale versus the non-log scale. If I say I have a pole at the origin, I'm referring to omega equal to 0. Omega equal to 0 is at negative infinity on a log scale.
I get that conceptually. I guess it's just the actual, because I'm guessing, I'm thinking of problem one. which-
So basically, don't think too. What I'm telling you in return is don't think that hard about it, right? What I'm saying is, if I have a pole at the origin or 0 at the origin, I go back to these building blocks. A pole at the origin crosses through 0 dB at 1 radian per second. Okay. A 0 at the origin crosses through 0 dB at 1 radian per second. That's it, right? And I just need to know that if I have a 0, it rises, pole, it falls. That's the critical thing to understand probably is those behaviors, and not to get too lost in the details there of what all that means. You need to be able to handle those building blocks and assemble those building blocks. Like, do you understand the process we just followed right here?
I understand it, and getting the output graph is a lot clearer now.
Yeah.
It's just, I was trying to follow what you were doing on like the graph I have for my problem one.
Mm-hmm.
And I'm getting mixed up with the pole at 0 and the pole at 1, because you said to start from the leftmost point. But it's like,
The leftmost point is at negative infinity if I have a polar 0
pole
there.
at 0, so you start over there, but then when I start analyzing my pole at 1,
Mm-hmm.
which is 10 to the 0, seems like do they then become 1, and is my pole, like my slope is now negative 40?
I don't know what the problem is. I can't answer that question exactly, but yeah, basically if I had, let's say I had a pole at, let's say I had S plus 1 over S, right? So that would be falling. And so this S guy here would be falling from negative infinity. He would pass through 0 dB at 1 and go down. This S plus 1 is a 0, so it would be flat, and then at 1 it would start to rise. So if I looked at the combination of those two things, it would fall at 20 dB per decade, hit omega equal to 1, and level off. We look at that separately after class. All right. Okay. So now let's say what I asked you is, we generated that complete graph. Okay. And now I said to you, all right, I have this input and I want to figure out the output V out. All right. So if I have cosines at those frequencies, all right, there's going to be, I don't know, some amplitude cosine 0.2t. There's going to be an output of that frequency, and there's going to be some phase angle. I'm not going to worry about the phase angle. All right. There's going to be another one at 200t. And it's going to have some phase angle. There's going to be another one at 5000t. Like that. Okay. So what we're asked to find here is what's the amplitudes of those guys. So A1, if I think about what A1 is going to be, A1 is the amplitude of the output at that frequency, 0.2 radians per second. So I would say that is the magnitude of the transfer function at 0.2 times 0.01. Okay. And A2 here would be what? What would A2 be? That's the
Transfer, the absolute value of the transfer function at 200 times 10.
Yeah. Times, 10. And then A3 would be the absolute value of HJ 5000. I think I multiply that times 100, like that. Okay. All right. Okay.
Where are the 0.1, the 0.01, the 10, and the 100?
Those are the amplitudes of the input.
Oh,
Yeah. Okay. So the idea is that it's always, the transfer function, the output amplitude is equal to the magnitude times the input amplitude at a given frequency. Okay. All right.
So to solve that, would we use -40 log base 10?
To solve that, we'd have to go back to the graph and we'd have to say, what's the magnitude in dB at those frequencies, and then get that out of dB. Okay. So the easiest one to start with here is probably the 200 radians per second. So I want to start with the 200 radians per second. The reason I want to start with the 200 radians per second is what's going on at 200 radians per second. Where is 200?
It goes to 0, or it just stays constant.
Yeah, 200 is there, and that graph is flat at that point. Okay. In fact, we said what it was there before. If we went back to where this guy was at negative 20 dB minus the 26.0206, like that, right? That was the magnitude at that point, okay? Which works out to be negative 46.0206, okay? So what does that mean? That means that 20 log magnitude of h of j 200 is equal to negative 46.0206, like that. Okay. You guys follow that? Any questions about what I did there? Okay. So if I want to find the actual magnitude, what do? I got to get that out of the dB, right? So this is negative 46.0206 dB, right? So that would be the magnitude of that would be divide both sides by 20, raise the result to the power of 10. So HJ 200 is equal to 10 to the negative 46.0206 divided by 20, like that. Right? If you do that math, that works out to be 10 to the negative 46.0206 divided by 20, 0.005. Okay, so this is 0.005. So that means that the output at that frequency, right, the A2 value would be 0.05. 10 times that, okay? So what that means is I put in a 10 volt cosine at 200 radians per second, and I got 50 millivolts out, okay? So it's been attenuated. I made it smaller, okay? So I'm filtering it, sort of, right? I'm making it smaller. That's the idea, okay? Questions about that? I looked at what was the magnitude of the graph at 200. So the magnitude of the graph was the y-axis value on that graph was negative 46.0206. So I read that y-axis value off. That's the easiest because it's flat right there. Now the next one I put in here, and this is what I think really kind of baked everybody's noodle last time, is this guy at 5,000. All right, let's say I do something at 5,000. Where's 5,000? Well, I don't know. That's a little tricky, isn't it? 5,000 is, I don't know, somewhere around like here, right? Somewhere around there. Okay. All right. So how do I want to try to approach that? Well, what's the slope? This guy is a line right here, isn't it? It's just a straight line. All right. What's the slope of that line?
-20.
Negative 20. Negative 20. I'll just go back to my basic linear algebra knowledge, right? I have essentially, let me get this, at that area. So at omega equal to 5,000, what I have is the slope, m, I'll call it, is negative 20. Now, just in terms of that's rise over run, right? Just in terms of basic linear algebra stuff, rise over run, okay? So for me, the thing that I do is I look at that and I say, well, all right, so if I want to figure out what's the run there, what's my x-axis maneuver? Well, if I know the value right here, right, at 2000 where it starts to fall, right, I know that value is negative 46.0206. What I want to do is how much delta y, how much drop did I do between 2000 and 5000? You guys follow that?
Yep.
All right, so my delta x is I'm moving from 2000 to 5000, but I'm doing it on a log scale. I'm linear on a log scale. So it's log 10 of 5000 minus log 10 of 2000. Right? That's how much I moved. All right? Because I moved from 2000 to 5000, but my scale is logarithmic. Right? So I just take that difference right there. Right? And I calculate what that is. All right? I don't know what that's going to be, but it's probably about 0.3 or something like that. Okay. Now, if I want to figure out how much I dropped, I'd say delta y equals m, the slope, times delta x, or negative 20 delta x, like that. You guys follow that?
Delta x is 0.3979.
Yeah. So I get the delta y. Then what do I do to figure out specifically the value at, so the y-axis value would be 20 log 10 of h of j 5000. How do I figure out that value? That's the y-axis value here. So I can think of that as, I'll just write that as my y value, right? Well, that would be whatever value I have on the y-axis over here at this point. If I want to figure out what that number is, I would say, well, I started at negative 46.0206, right? And I added a delta y to that. Okay. So I started at this value and I added a delta y to that. So let's go straight over to MATLAB to try to calculate that. Okay, so what did I do here? All right, here's my delta x. Now in MATLAB, if you do this, the command log means what to your calculator ln is. Okay, so I always say log 10 because of the fact I'm trying to very explicitly tell you what I mean is the base 10 logarithm. All right, so in MATLAB that's log 10. Okay, so I say log 10 of 5000 minus log 10 of 2000. That's a delta x value. My delta y value is negative 20 times that because the slope was negative 20. And then I basically take that negative 46.0206 and add that to my delta y. All right, so let's compute that. That works out to be negative 53.9794. All right, negative 53.9794. That's my dB value there. Okay. It's not the magnitude, that's my dB value, right? So how do I get my magnitude? Divide by 20, raise both sides to the power of 10. So I would say 10 to the negative 50, what do we say it was 53.9794. 9794 divided by 20 is equal to the magnitude of that guy at 5,000. All right, and that works out to be like 0.002 or something like that. So I'll do 10 to the y over 20, 0.002, right? 0.002. So that's the magnitude of 5,000, okay? So the amplitude of the output at that frequency, I put in a 100-volt waveform, at 5,000. What's the magnitude of the output?
0.2.
Well, it's 0.002 times 100, right? So that's 2 times 10 to the minus 3 times 10 to the 2, which is 0.2, right? You guys follow that? All right, and then at 0.2, I would do something similar, right? At 0.2, it's right here, right? So that guy, you know, is somewhere around 10-ish dB if I look at where that is. But if I wanted to figure that out, what I would do is I would say, well, I could pretty easily figure out what this point is, right? This point right here started out at, right? It started out at -40, and then it shifted down -26. So this guy is -40 minus 26.0206, right? And I could figure out what the value is at that point exactly. And then I would have to say, well, what's my delta y here and my delta x? So as I go from 0.1, where I know the value, to 0.2, the delta x there would be log 10, 0.2 minus log 10, 0.1, right? You guys follow that? I know the slope is -20. So -20 times that delta x tells me how much I've dropped. Okay. You guys follow that?
Is the 0.2 just the? Oh, hold on, never mind.
Yeah, 0.2 is the other frequency where I said I had an input, right? All right. You guys follow that? So it's,
Yep.
I had a transformer example. Obviously, we're out of time to do that, but we can do that Wednesday. It's fine. Okay. All right. Hopefully this helps to understand what's going on in the homework. Problems 1, 2, and 3 are the most important things in the homework, right? Because there's going to be Bode plot problems on the test. All right. The solutions from 9 are posted so you can take a look at those. All right. If you didn't finish those. All right. But definitely dig into those problems because you're going to need to know how to do those for the test. Okay.
By hand, correct?
What's that?
You want us to do it by hand instead of MATLAB, right?
Yeah. I mean, so you need to be able to generate the plots by hand, right? Because you will be asked to do it by hand on the test.
Okay.
All right. Any other questions online? All right. I'm going to stop here.